Okay, so I'd like to give you some sort of a physical picture for why we can have why would a conformal field theory be the correct description of the continuous phase transition. So this point where the magnetization is just starting to appear as we lower the energy. Okay, so I'm going to think about a 2D Ising spin magnet. So what that means is I'm now going to distribute my spins all over the plane. So let's imagine that, so I'm just starting to form magnetization. So I'm very close to the critical point. And what happens is the spins are starting to align. So I've got this region over here. There's a clump of spins and they're all pointing up. And let me draw them as that circle. Okay. So inside that circle, everything is pointing up. They're starting to align. And in fact, I might find that there's another region just like that, sitting nearby. And maybe even another region just like it sitting nearby. But these three are actually part of some bigger droplet. And inside this bigger droplet, all of the spins are pointing down. Okay. But we wouldn't just have one of these bigger green droplets. We may have many of them. So let's take this one and we'll put another one over here. And maybe another one over here. But these green droplets are themselves part of an even bigger droplet. Sorry, sitting over here. And, oh, actually, I wanted a different color. So let me go for red. Part of an even bigger droplet sitting over here. And inside this even bigger droplet, now the spins are all pointing up again. Okay. But now there's many of these red droplets. So I've run out of page on my iPad, so I can't draw another red droplet, but there would be many of these red droplets, and they would be sitting inside an even bigger droplet, maybe a purple droplet or something that outside of these red droplets, all of the spins inside the purple droplet are pointing down. And so it would continue on and on like this. So what has happened? Okay, what has happened is the following. Sorry, I want this boundary to be green. Okay, oh, that looks pretty bad. Let's see, can I? Oh, that's better. Okay, so now, how could I think about this? Oh, okay, my colors are not the best. So, but I do want the colors to be correct. So, good. Okay. Now, what you should think is on the smaller scales, okay? So the scale of the black droplets. On the scale of the black droplets, we've got all of these black droplets, and you can study the distribution of these black droplets. And these black droplets sit inside slightly bigger green droplets, and the green droplets sit inside slightly bigger red droplets, and so on. So we could study things on the scale of the black droplets. Or we could choose to pick a bigger scale where now we're studying things on the scale of the green droplets. So now at a bigger scale. And on that bigger scale, we could ask, well, how big are the green droplets? What's their distribution? They're surrounded by bigger droplets, and those themselves are also surrounded by bigger droplets, and so on. And what we find is, if we look at the scale of the black droplets or the scale of the green droplets, The number of droplets, how they distributed, how they sit inside each other is exactly the same. And then if we change the scale to be even bigger, so we study things on the scale of the red droplets, again, the red droplets are distributed exactly as the black droplets were and the green droplets were, and they're inside bigger droplets and they sit inside the bigger droplets, just like the black ones sat inside the green ones, and so on. So if you study the system at any scale, because of this droplets inside droplets picture, we land up getting scale invariance. So this is the picture that you should have of how at this critical point we get scale invariance. And the scale invariance combines with the other symmetries of the system to give us a full conformal symmetry. So that's the picture that I want you to have about scale invariance. And that's how at this critical point we land up getting a description in terms of CFTs. That's how scale invariance spontaneously appears, and it's why a CFT is relevant. Now, this critical point occurs at some critical temperature Tc. So we might ask, okay, good. So now we understand how scale invariance appears, and well, it's plausible that we get a full conformal symmetry, but what can we calculate using the conformal symmetry? So now I'd like to describe some of the things that you could actually calculate. Okay. So in terms of this critical temperature, Tc, I want to define a new variable. My new variable is tau. And what is tau equal to? Tau is just T minus Tc over Tc. Okay, so I'm defining this new variable tau, and I'm going to use that a lot. So tau is actually equal to 0 at the critical point. Just above the critical temperature, tau is positive, and just below the critical temperature, tau is negative. So tau is going to be the variable that I'm going to use instead of the temperature. But when I'm telling you how things depend on tau, I'm telling you how they depend on the temperature. So one thing that you could look at is you could look at, say, the magnetization. And we'll look at the magnetization as a function of tau. And what we find is for small tau, so that's when we close to the critical point, this behaves like tau to some power, let's call that nu. Okay? And nu is not an integer, it'll be some number that we would like to calculate. So you'll go into your lab with your sample of spins. And you'll have to tune things very carefully in the lab to get to the critical point. But once you've tuned it, one of the things that you could measure would be the magnetization. And when you study the magnetization, as you go towards the critical temperature, the magnetization will vanish, but it'll vanish as some power law. So you can actually measure nu. So this is something you could actually measure. It has a name. It is called a critical exponent. So you would like a theory to predict the value of the critical exponent. Well, one of the things that you can do with conformal field theory is that you can calculate the value of the critical exponent. It's not just the magnetization that obeys a power law of this type. Many other quantities would. For example, the free energy would, the specific heat would. So all kinds of quantities associated to your system would obey these power laws. Each of them would have a different critical exponent, and you would use the conformal field theory to calculate these critical exponents. That's one of the things that you could calculate with the conformal field theory. Another thing you could calculate with the conformal field theory would be a correlation function. So let's take the value of the spin at position x. So position x would be some site in our spin magnet. And we could look at the position of the spin at site y and then calculate the correlation function. So these angled brackets means you're taking an average. You're averaging over all of the states. Now, this is close to the point where entropy is winning. So you've got the same number of spin up as the same number of spin down. So you'll have an enormous number of states. For each state, you work out what is the value at y, what is the value at x, multiply them, and then you would average this over all possible states. So that's what the correlation function is. Now, what is the correlation function telling you? Well, if you're at position x, so let's imagine that position x is over here, the spin could be up or down, okay? And if you're at position y, the spin could also be up or down. If the correlation function was a very large positive number, then whatever the spin at x is doing, the spin at y will do exactly the same thing. So the correlation function is telling you exactly what it says. It's how x, the spin at x and the spin at y are correlated. So a positive number tells you that those spins would point in the same direction. If you get a negative number, then it tells you that most of the time when the spin at x is up, the spin at y will be down. And what I mean by most of the time, that means for most of the states in the ensemble, if the spin at x is pointing up, then the spin at y will be pointing down. And if the correlation function is 0, then the spin at y is not really correlated. It doesn't really care about what the spin at x is doing. So if the spin at y is pointing up, half the time the spin at y points up, and the other half of the time the spin at y points down. So when you average this quantity, you'll end up getting a naught. Okay? So that's what the correlation function tells us. Now, in a conformal field theory, if you go ahead and you calculate this correlation function, what does it look like? Well, it takes the following form. So there's some constant. That's not very important. You can swallow that constant into a normalization of whatever field you're looking at. So in this case, the spin field. But what it looks like the mod of x minus y, and then we've got some power here to delta. Okay, so the correlation function looks like a constant over the mod of x minus y to 2 delta. So delta sets the power law. This dimension delta, so the dimension delta, and this actually is the dimension of the field. We'll see that later on. So later we'll prove that conformal symmetry forces the two-point correlation function to be a power law. And this is actually related to the anomalous dimension of the field. So the dimension delta is also something that you would calculate using the conformal field theory. And you'll have a power law of this type for every single different type of local field in the theory. And the conformal field theory would give you a way of calculating all of these power laws, all of these dimensions. Good. So here's a summary. So what have we been studying? We've been studying the critical point of the Ising magnet. So this is just when, this is at the point where the energy entropy competition is balanced, and it's just at the temperature where if you lower the temperature to Tc, now magnetization is starting to form. And the way that it forms is little droplets of spin start to point in the same direction. And you've got little droplets inside bigger droplets, which are themselves inside bigger droplets, and so on. But these droplets, statistics of them, how many of them are there? How are they arranged? What are their sizes? The kinds of statistics of the droplets look the same at any scale that you look at the system. So the system develops a scale invariance. And because of that, it develops a full conformal invariance. In terms of this parameter tau, which was normalized so that it vanished at the critical temperature, we could study many functions, many physical observables as a function of tau. And we said that things like the magnetization, the specific heat, the free energy, they obey some power law as a function of tau. So they behave like tau to some power. That power was called the critical exponent, and a conformal field theory will tell you how to calculate those critical exponents. The conformal field theory is the theory of those critical exponents. And then in addition to that, we could take any local field and calculate correlation functions. Two-point correlation functions has this nice power law dependence, and the power of that power law, which I parameterized as delta, this is related to the dimension of the field. And again, the conformal field theory will give us a way to calculate those dimensions. Good. So this is why conformal field theories are relevant for continuous phase transitions. And we're going to be saying a lot more about this with details when we actually start to do some calculations. But next, let's just say a few words about quantum phase transitions.